The definite integral. We start with this thing called the fundamental theorem of calculus, which is basically what we looked at yesterday. You integrate the integrand to get the primitive function. It's essentially what it's saying. Okay. Some properties of our definite integral. This is basically what we've been looking at so far, because we've just been looking at polynomials. Add 1 to the power over the power. But now we've added in this notation of the integral symbol. We're integrating from a to b. We always substitute the top number in first minus the bottom number. Now, it doesn't mean that the top number has to be the biggest number. It doesn't have to be the biggest number. But it's always top number minus the bottom number. When we factorise, you can only factorise out constants. That's essentially what this one's saying. So if you want to factorise outside the integral sign, you can pull constants out, but you can't pull out pronumerals. The third one, similar to differentiation, is basically saying you can integrate each bit individually. Fourth one, this is an interesting one. And you might think, well, what's the point of this? If you're integrating from A to B, you could, if you wanted to, integrate from A to C and then do another one from C to B and add those two together. If the function is positive, then we know the answer for the integral will be positive as well. If the function is negative, then the integral will be negative. Function x is less than g of x, then their integrals will also follow that pattern as well. And this one here allows me to swap the limits around. Some people like to have the bigger number on top, so we leave it as a to b. Some people like to have it on the bottom. Well, swap it round and make it the negative. Because if you think about it, it's the top one minus the bottom one. So if you wanted to swap them round, you'll get the negative of the answer. So you need the negative sign out front. If you've got an odd function, then the integral from minus a to a will be 0. If you have an even function, you can do twice from 0 to a. Why do that? Often 0 is an easy number to substitute in. Now, when you're working out odd and even functions, keep in mind, if you've got functions multiplied or divided for that matter together, odd times odd is even times even is odd, even times even is even. So basically, same type of function multiplied together gives you an even function. Different types of functions will give you an odd one. All right, let's do some examples and see what all this means. So I've got the integral from 1 to 2 of 6x squared. I could, if I wanted to, factorise the 6 out and just integrate the x squared. Add 1 to the power over the power, x cubed over 3, the 3 and the 6 cancel, substitute in 2, substitute in 1, we get our answer. The second one here, it's in, surd form. So before I integrate, I need to put it into index form. So be careful with this, add 1 to the power over the power. A third plus 1 is 4/3, so we end up with 3/4. You sort of turn the fraction upside down out the front. So 3/4 x to the 4 and 3. We're going from 5 to 0. Well, x to the power of 4/3 is the same as x times the cube root of x. 4/3, 1 and 1/3. That's going to be easier to substitute into because 5 to the power of 4/3 is not going to be a nice, neat, exact answer. So when I have it as x times the cube root of x, it becomes a bit easier because I know I've got 5 times the cube root of 5, so I end up with 15 times the cube root of 5 on 4. You won't get that exact answer by just plugging it into a calculator. Whoa, sine. We haven't seen how we integrate or differentiate sine. So what on earth is this doing here? Well, notice the symmetry, minus 2 to 2. Sine is an odd function. I got it to the power of 5. So I'm going odd times odd times odd times odd times odd. What do I end up with? Well, odd times odd is even times odd is odd, then odd times odd is then even times odd is odd, and I think that's where I'm up to, isn't it? Now here, I can simplify the integral a bit by playing with symmetry, because see now I'm going from minus 1 to 1. I know all of the odd functions will be 0, so I should get the same as this. I don't need to worry about the odd functions, they're going to be 0. So I'm left with 2x squared plus 1, but plus I can go twice from 0 to 1, because I've got an even function left. So that allows me to do 2/3 x cubed plus x, sub in the 1, sub in the 0, 10/3 we get as an answer. This is an interesting thing. Sketching the signed area function. So this is what's called the area function. going from a to x of some function comes up with the area under the curve. Okay, we will get function x minus function a, whatever the primitive function happens to be. Here's a graph of our function. We now want to graph the sine area function. How do we do it? To make life easy, I'm going to tell you what all those areas are equal to, and to make it real easy, I'm going to make them all equal to a. So every piece here is going to be a. Okay, so I've got 4 a's there. Okay, above it, I will now draw the sine area function. So a, that x-intercept, I'm going to plot it. Area A must be equal to 0 because have a look at the formula. It'll be function A minus function A, which of course is 0. So I know I can plot that point. It's an x-intercept. What that therefore means, this curve I'm about to draw is going to be a stationary point because its derivative, remember the second one down is the derivative graph, the derivative at A is equal to 0, and we know stationary points happen when the derivative is equal to 0. Now, what about the 0? What happens there? What's its value going to be? So we're now saying, what's the integral from A to 0? Well, looking at my picture, I know the integral from 0 to A. I'll swap the limits, but I've got to put a negative sign out the front. Therefore, it must be negative A. So I'll plot negative A. Let's work out B. Area B turns out to be negative A. Why? Because it's function B minus function A. What is function B? Function B would be going from A to B, which is A, but it's underneath, so it's negative A. So that's from A to B, and that's what we want, isn't it? Because our formula says what is it going from A to B. So I can plot that. This one therefore means that B will actually be a possible point of inflection. You really got to think through this one. Because the second derivative, if we were to draw it, would be the first derivative of this one. Now, look at B, I have a stationary point on the derivative graph. So the second derivative, it would be 0. Second derivative means possible inflection point. Let's have a look at C. So going from A to C, we've got 2 below, which is minus 2A. Plot that. Right. Also means C is a stationary point, because look, on the derivative graph, it's equal to 0. Area D will end up being negative A, because if we go from A to D, we've got minus 2A below, we've got A above, put them together, you get negative A. Look at those dots, we're starting to see what the curve's looking like. Notes, in the interval from C to infinity, our derivative is continually increasing, because it's getting more and more positive. Therefore, our graph is increasing because our derivative is always positive, and we said that defined an increasing function. There is the area function. We will spend a bit more time later, in a few topics' time, looking at drawing derivative graphs and things like that in a bit more detail. All right, there we go.